Thank you so much for coming to the fourth lesson in the module LTCC module maximum entropy of network ensemble. Today we will cover the lesson will have two parts as usual. And we will cover in general ensemble, maximum entropy ensemble, which go beyond the degree, the constraint of the degree sequence. So in the initial three lessons, we have covered extensively the case of network random graph and network with given degree sequence. Today we want to go beyond. And in the first part in particular, we will cover structural constraint. And we will start with a slight modification of enforcing a given degree sequence. So we will start by considering what happens if I do not have the label of the node. So if I want only to enforce a given degree distribution, how can I do that? And what is the entropy of the ensemble with given degree distribution? And then we will discuss a bit a challenging problem of modeling and generating networks with expected degree correlations. And finally, I tell you a little bit about what happens when the constraint, the structural constraint on the network are not linear in the adjacency matrix. So until now, you've seen as constraint the degree of each node, the degree sequence. So the degree is the sum of the row of the adjacency matrix. So it's a constraint which is linear in the adjacency matrix. And we will study how the model, the maximum entropy model might be much more complicated if we consider non-linear constraint, as for instance, the number of two stars that are triple of nodes connected by two links. And we will study, I will mention also the Strauss model, which is instead the model in which I want to constrain also the number of triangles in the network. And as you will see, that there will be a lot of surprising results, including phase transition and coexistence between different spaces. So in part two, instead, we will take another approach. We will go beyond the constraint on the pure degree sequence, but we will consider still linear constraint, but linear constraint which take into account latent variable associated to the nodes. So the nodes can have a position in space or any feature associated to the node that you want to input as an important aspect of determining the network structure. And we will cover in particular spatial networks of different type, including soft random geometric graph and this soft random geometric graph in hyperbolic space. So the references are the book of Mark Newman always. Newman has been working a lot also in this two-star model, which is also featured in his paper with Park in 2004. And yes, regarding this latent variable, second part, I've been writing a chapter of a book, which I hope will be soon available in the archive, but this might take a little bit of time, There are several references, but this point of view, which I will present, is somewhat my personal view on the topic. So let's start with part one. So as I said, we have covered extensively ensemble of a network with given expected degree sequence, or with given given degree sequence. How would we go around for modeling network with given degree distribution? So in which I don't know which node has which degree, but I only know the distribution of the degree in the network. So as a reminder, of course, this is practically well understood at this point. The entropy of the ensemble is defined as the Shannon entropy constructed starting from a probability of having a given graph in the ensemble. And this maximum entropy ensemble maximizes the entropy given a set of constraints. So here I want to tell you to express the entropy of a network ensemble in which we consider a given degree distribution. So, and I want to show you that the entropy of this ensemble is the entropy of any network with a given degree sequence, any degree sequence satisfying the belonging, corresponding to the degree distribution that we want, plus an extra term that corresponds to practically the number of ways in which we can realize a given degree sequence given a degree distribution. And if for large network size, so for a large n, this entropy can be simplified by this expression where pk is the degree distribution of the network. So I want just to briefly show this derivation. So if I have a graph and I want a graph to have a given, I want to have the probability of a graph where the constraint is that the node have a given degree distribution, what I can say that is that the probability of a graph is the probability of a graph given that I impose a given degree sequence on the node multiplied by the probability that I observe that degree sequence. Okay, so this is a conditioning on the degree sequence of the node, and this expression is valid in general for any ensemble. Okay, so I want to consider the entropy of an ensemble, which is defined in this way. So what I do, I can input the expression of P of G, in which I first condition on the degree sequence, and then I write the probability of a given degree sequence. Okay, so I just rewrite the definition of the entropy using this expression for B of G, in which I condition on the degree sequence. So now, when I have this logarithm, I have the logarithm of P of G conditional on the degree sequence multiply P of the degree sequence. I can write the logarithm as the logarithm of the first term plus the logarithm of the second term. So I will have sum over all and I also the sum over all the graph. I can write it as the sum over all the degree sequence given a given degree distribution, and then the sum of all the graph that satisfy that degree sequence. Okay, so when I express the sum over G in this term, and when I write a logarithm of P of G given the degree sequence multiplied by P of the degree sequence as the sum of the logarithm, I can express this quantity in this way, okay? So this is straightforward, just if you try to, so here is the logarithm of the first part, here is the logarithm of the second part, and here I divided a bit this sum over the degree sequence condition on the degree distribution and the sum over all the graph conditioned on the degree sequence. So now, if you look at the first term, you see that essentially here you have an entropy of a network given a degree sequence, okay? But all the entropy of the network given a degree sequence are the same if the degree sequence are only differing from permutation of the label of the nodes. So this first term is just the entropy of the network with given degree sequence. And the last term, given that this quantity is normalized, is just given by practically the entropy associated with the probability that I observe a given degree sequence given a degree distribution pk. Okay. So it seems complicated to explain, but if you use pen and pencil and try to do the step, it's quite easy. So now we have this expression, and we notice that the probability of observing a given degree sequence when this degree sequence is drawn from a same degree distribution is just the inverse of the number of ways in which you can achieve a degree distribution, a degree sequence starting from a given degree distribution that is given by this multinomial distribution. And then practically you insert this definition inside here, the entropy associated with the number of ways in which you can realize a degree distribution, and you get this expression. This is the answer we wanted to have. And if you use a Stirling approximation for factorials that is valid for large n, then you, by doing this explicitly, you see that you can approximate the entropy of a network with a given degree distribution by the entropy of the network with any degree sequence corresponding to that degree distribution, plus a term that accounts for practically the entropy associated with the degree distribution itself. Okay, so this is essentially the way in which you can express the network with given the entropy of the network with given degree distribution. And interesting, if you consider this ensemble, you find that the marginal, so the probability that I connects to J is given by the sum over all the degree K and K prime. The probability Pk K prime that I is connected to J, given that I has degree Ki and J has degree K prime, and multiplied by the probability that one has degree K, which is P of K, and the other has degree K prime, which is P K prime. So it's just, you express Pij and you condition on the degree of node I and J, and you have this expression. So this probability now is independent on the labeling of the node I and J, and therefore this this model now becomes exchangeable. Okay, so it's independent on the label of the node. In fact, we are enforcing the degree distribution, not anymore the degree sequence. So practically we don't take into account anymore the identity, the labeling of the node. Okay, so this is a fast way in which we can try to go behind constraining the degree sequence, so forgetting the label of the node. Another thing that we can do is try to enforce degree correlation. So we have seen that the configuration model and also the canonical ensemble with given expected degree sequence has some natural correlation. But in real network, you observe also correlation that are assortative, so that cannot be in any case generated with this natural correlation, or also disassortative, but more severe than what we observe in natural correlation. So there is a general problem that you want to model a network with given degree correlation. Why should you do that? Well, you should do that because maybe you are interested in simulating a dynamics on this network and checking whether the dynamics is different from in a network with control level of degree correlation respect to a network in which, for instance, you don't have correlation. So you respect to a network that is uncorrelated. Okay, so there is a lot of interest in the relation between dynamics in a network that is uncorrelated and in a network that is more and more correlated. So for instance, including degree correlations. However, so what you want to do is to have, for instance, some set of R constraint. So you have the degree of each node, and then you want to enforce practically the matrix of correlated degree. So how many link connect a node with degree k with a node with degree k prime. So you might want to do that. And actually, this is a quite of an hard problem. And there are algorithms to do that. And I point you to this paper by Basler et al. However, often these Monte Carlo methods have produced an ensemble which is biased. It's not the maximum entropy ensemble. So it has some bias that are imposed by the way the network are constructed. Okay, so another way to go around that is to have something a little bit different from what we discussed so far. And you can indeed combine practically hard constraint with soft constraint. So you can have practically an ensemble in which you fix the degree of each node, and then you have a set of soft constraints in which you impose the expected number of links between node of degree k and node of degree k prime. And you can generate this network using, for instance, the Metropolis Hastings algorithm, or a variation of this, of the algorithm that I described to you in the previous lesson. So regarding the theoretical approach, so what is the probability of a network in this ensemble? Well, you have a set of R constraints, so you have the delta on the degree of the node. And these delta are really fundamental because, and then you have a set of soft constraints, which are the expected number of links between nodes which have degree k and nodes that have degree k prime. And as I mentioned, the R constraints are really fundamental because this constraint of the number of links between node of class K and node of class K prime is only defined if we really know for sure what is the degree of node I and the degree of node J for every I and J. Okay. So, so how can we treat a mixture of soft and hard constraint? Well, we have an hard constraint, which is the degree of each node, which implies that the probability of my network will be greater than 0 only if the degree of each node is what I want. And for my entropy of the ensemble can be expressed just as a sum over the graph G, such that that you have a given degree sequence, the one you want to impose. So, so practically your entropy can be also written in this way, where instead of the probability of a graph, we indicate the probability of the graph given the degree sequence, because a graph will have non-zero probability only if it has this degree sequence. So we have this constraint that this probability of the network given the degree sequence is normalized, and we have a set of soft constraint enforcing the expected number of links between node with degree k and node with degree k prime. So we, in order to find the expression for the probability of the graph, we just proceed as we have done previously, but now we work practically exclusively on graph with given degree sequence, and we only impose practically the soft constraint on the expected number of links between nodes of different degree classes. And by doing, the standard calculation that I've been doing all along in this class, we find that this probability of a graph given the degree distribution is just this, takes just this exponential form, where z is the partition function, and finally we can express the probability of any graph by imposing that only graph with the degree sequence that we want are allowed, so a probability greater than 0. So you see, it's possible to have a mixture between soft constraint and hard constraint, and this can be a powerful tool to solve hard problem, because otherwise having both hard constraint can be quite challenging, and having an algorithm that is unbiased for the moment has not been possible. Okay, so we have covered this different variation and different constraint on the structural constraint on the ensemble, going beyond just the given degree sequence. But for the moment, we only consider constraints which are linear in the adjacency matrix. Also, when we fix the number of links between nodes of different degree classes, this is just a number of links, so it's linear on the adjacency matrix. What I want to now to tell you is what happens when the constraints are nonlinear. And what happens is that you can observe interesting phase transition. And the analytical results are much more limited. So you can get analytical results in the mean field approximation, which can be important to tell you what is going on, but then to solve exactly the problem, it's very challenging. So what is done typically is to solve this ensemble numerically. So the first example of a nonlinear mode constraint is what is called the two-star model, in which you constrain the number of two-star or wedge, which are these structures, so a triple of node connected by two links. So you want Aij to be equal to 1 together with Ail equal to 1. Okay, so you want a star in which Ai is the same here. So so in the two-star model, what you want is to fix in the canonical ensemble the expected total number of links, which is a linear constraint, but also the expected number of wedges, which is a nonlinear constraint because it goes like the adjacency matrix to the square. So mathematically, so we have seen many times how to constrain the expected total number of links is just the expectation over the probability of the network of the sum of all the elements of the adjacency matrix of the triangular upper part of the adjacency matrix. And then when we want to fix the total number of wedges, we need to fix in average the sum over I of all triplets of all wedges. So we need to multiply to sum over J and L these terms that are, quadratic in the adjacency matrix. And this will cause us problem, okay? So we will see, and in particular, problem or beauty, depending on the point of view, because it leads to phase transition in the structure of the network. So it leads to phase transition, a phase transition in which you have a transition between a low density phase and a high density phase, including a region of the phase space with consistence of two phases. So that means that there are some parameter value or some constraint in which you can have two solutions. One solution in which the number of links is high, and one solution in which the number of links is low. So let's see. So this is a canonical ensemble. So practically the probability of the network is just given by the well-known exponential form in which we have a first Lagrangian multiplier, which we call lambda, and then the f of g that fixes the number of links, the constraint. And then we have the second Lagrangian multiplier, and then the structural expression of expressing the constraint on the number of wedges. Okay, so we can write this as e to the minus h, where h is the Hamiltonian divided by the partition function. So we are in particularly interested on this, this expression for the Hamiltonian that, as you see, does not only include the linear term, but also a nonlinear term that is proportional to the product of two elements of the adjacency matrix that share one index. So this is in general, to find the partition function of such a problem is in general a hard problem, and some of you might have been encountered a kind of similar situation where in statistical mechanics model, for instance in the Ising model, where you have just variable that are associated to a single node, like a spin. You don't have a variable with two indices. You have just a variable with one indices. But when you have the product of two variable with two indices, then the treatment of the statistical mechanics model might become more complicated. And in this situation, you have to rely on some approximation. And one very useful approximation is the mean field approximation, in which practically your goal is to reduce this non-linear term in a series of linear terms. And how would you do that? You take the first elements and multiply by the expectation of the second, and then you take the expectation of the first and you multiply by the second, and then you need to subtract by a constant factor, because which is the expectation of both elements. Okay, so what does this expression in some sense? It is an expression which allows you to neglect correlation between this the value that this matrix element can take. In fact, if you do the expectation of the left-hand side, you have the product of the two expectation twice minus 1. So this is practically the expectation of the product of the two adjacency matrix element is equal in this approximation to the product of their expectation. So what we are really doing is you are saying that these variables are not correlated. So you are neglecting the correlation. Okay, so this is a well-known approximation used in a number of situations, but this is how it applies to this problem. And in our problem, we also have in some sense a simplification, because as you see here in this constraint, these constraints are global. Okay, so you fix the total number of links in the graph, you fix the total number of wedges in the graph, and this is revealed by the fact that also the Lagrangian multiplier are local, they don't depend on I and j. And in this situation, we don't expect one element of the adjacency matrix acting very different from another element in average. And therefore, we can assume that in average, every element of the adjacency matrix will be equal to a quantity that we call P, or connectance, or probability of a link. Okay, so every pair of nodes will have in average the same probability to be connected. It's a bit like in a random graph, you know. But as we will see, this probability satisfy an equation which allows to find in some region of the space two solutions. So you don't have only one solution, but you have two solutions. So when you insert this expression P in the mean field approximation, so you remember you express the product of the two adjacency matrix elements, like the first multiply the average of the second, P, and then the second multiply the average of the first, P, and minus the average, the product of the two average, so P squared. So we have originally this Hamiltonian, but we can express this Hamiltonian in this approximation. And so the first term remains unchanged. The second term, we substitute the mean field approximation for this product. And what we get is a term that is linear now in the adjacency matrix. And it depends on the Lagrangian multiplier, beta and gamma, but it depends also on P itself, okay? And then we have a constant. This constant is not generally a problem because a constant in the Hamiltonian, it cancel out when you measure the marginal, and you can see this directly if you try to do the calculation. So, so you have this mean field expression of the Hamiltonian, and then this is just linear in the adjacency matrix. So if I calculate the marginal P, which is the average, the expectation of Aij, I get a function which is my familiar, logistic expression, where I have this term which is beta for n gamma p here. Okay, so this is different from what we were observing in the random graph, because in the random graph, practically, we didn't have this for n gamma p, so gamma is equal to 0 in the random graph, okay? So now we have a marginal, which is expressed in terms of the Lagrangian multiplier and the marginal itself, okay? So how can we solve that? Well, we can plot the function p here, which is the left-hand side, and the function f of p, which is the right-hand side, which is this either red, green, or orange curve. And we can look at when these two functions coincide. So you see, for the orange curve, you have just one solution for very small value of p. For the red curve, you have only one solution for very high value of p. So meaning that you can have a transition between a low connectivity, a low density network, and a high density network. But relevantly, if you consider a parameter value consistent with this green curve, you see actually three possible solutions. So if you study the stability, you see that only the low P and the high P are stable, but well, you have here that for a given number of parameters, you have two possibilities. Either the network is in a low density region or is in a high density region. So practically, you can rename this combination of Lagrangian multiplier beta and gamma n as B and J. And this name reminds us of the very strong similarity of this model with the Ising model. And then you see that, you know, for low value of J, you have you go from small connectivity to high connectivity network by increasing the B, which enforce the number of links that you want in the network. And if you increase J, this transition becomes steeper. But then if you increase J over a given threshold, you find two curves, meaning that for very here for very low negative value of B, you have a low density network. And for very high, you know, if you raise B, you have very high density network. But in this region in between, you have actually two solutions. You can either stay here in a high density regime, or you can stay here in a low density regime. So you see that as you change J, there is this dramatic phase transition in which in one case you have only one solution, in the other case you might have a coexistence of two different phases for the same parameter value. So this is quite significant, but the two-star model is actually the easier model with nonlinear constraints, and a more complicated model, which is actually very interesting and fascinating, because actually something you really, in a number of cases, you really want to do, is the Strauss model, in which you constrain also the number of triangles. So the number of triangles is the number of triple of node connected by 3 links. So you must have that Aij is 1, AJL is 1, and ALI is 1. The 3 matrix elements should be 1 at the same time. So this product should be 1 to have a triangle. And in the Strauss model, you really fix the expected total number of links and the expected total number of triangles. So now you have a constraint which is of order 3 in the adjacency matrix. And so you have the constraint on the link, which is familiar, and the constraint on the triangle, which is this. You constrain all the number of triangles in the network in average. And this model is quite complicated, so we will not cover it. And you have a first order phase transition between a low density phase and a high density phase. And this includes a region of the phase space with a coexistence of the 2 phases. And most relevantly, this model display quite a particular phenomena, which is a condensation phenomena, meaning that in the high density phase, you observe the network decompose in 2 parts. In one part, you have a very high density phase with a lot of triangles because you have a high click, and then you have many disconnected nodes. So you, in order to satisfy the constraint of having many triangles, the network chooses to have very large clicks, which have a lot of triangle, very densely connected, and then several nodes that are totally disconnected, node and cluster. So this is a very special model and very interesting, a way to deal with this, like the composition of the network, is to impose numerically a local constraint on the clustering coefficient. So you want to constrain the number of triangles locally for each node, and in this way you avoid to have the triangle all condensing in a specific region of the network. So this concludes the first part of today's lecture. So we have seen several examples of constraints which go behind the constraint of just having a given degree sequence or expected degree sequence. And these are constraints imposed by the structure of the network. So we have seen how to enforce degree distribution and how to enforce degree correlation, mixing hard and soft constraint. And then we have seen how nonlinear constraint in the adjacency matrix can lead to, first of all, some kind of untractability of the model, but then this model can be tackled with a mean field approximation, and you can see that actually they display phenomena that are particularly new, and in particular you observe this coexistence of 2 phases, so that given a number of constraints, you can have 2 possible solutions, 2 possible scenarios of network realization. So this concludes this first part of the lecture. And let me just stop the recording.